Hello everyone attending this virtual IGCP meeting. My name is Antonio Klein. First, I would like to thank Professor Christopher Ryan for the invitation to participate to be in this virtual event. It's an honor for me. Second, I hope you can understand my English and my Portuguese accent. This is the title of my presentation, CASI, Coastal Analysis System from Space Imagery Engine, a satellite image data cube in coastal science, tools for monitoring, boundary condition definitions, and management. This is the agenda that will be presented in the next few minutes. I will start with motivation and definitions. Then I will present the CASI core platform and some modules with an example of what can CASI do for you. At the end, I will conclude with a summary. Between 2014 and 2017, I developed a project with the aim of defining and testing a methodology for the quantification of coastal hazards and projection of future coastal lines to support coastal zone adaptation studies on the northern coast of Santa Catarina Island and surrounding areas. During the project, I tested two well-known methodologies in the international literature, Ferreira et al. 2006 and Salinger 2000, in order to perform forecasting based on hindcasting using the worst-case climate scenarios and impact on the beach. But we found a series of issues like a lack of metadata in the data, as well as a lack of the data itself. For example, wave climate and the total water level, shoreline evolution, topography and bathymetry data or digital terrain models. And at the end, how to apply the different methodology in a large scale. Or what is the approach for addressing this on the 8,000 kilometers of Brazilian coast? The solution was use a satellite image data cube, which refers to a multidimensional data structure used to store and manage large volume of satellite image data, where it organizes satellite images based on dimensions like time, location, spectral bands, and other parameters, facilitating efficient storage and analysis for various applications such as coastal science. The question now is, why use satellite images? Well, because there are near 40 years of satellite image database publicly available for Landsat and Sentinel-2 missions. The use of this database may improve the knowledge about coastal process over different time and space scales to provide data that can be easily used as a boundary condition or a reference to calibrate numeric models for forecasting future coastal scenarios. And the next question is how? Well, using the data cube to produce read data. To do that, we chose firstly the Google Earth Pro, but just in time, 2017, it was available the Google Earth Engine, that is a planetary scale geospatial and friendly web platform, where there is a big data repository of satellite images and tools for cloud processing. And we only need at that time to develop the front end, the CASI platform. The CASI platform is an opportunity to develop open source software tools to train human resources, to promote collaboration to share information, to generate public database for managers of different levels. As a result of the potential demands, we formed a consortium to develop CASI, the front end, with the participation of different universities of Brazil and outside of Brazil, foundations and public and private companies, primarily supported by the Council for Scientific and Technological Development of Brazil, CNPq, and Boticário Foundation. More information are available at the web page of CASI, casiengine.org, and the codes are available at Federal University of Santa Catarina GitLab. At this moment, there is an interdisciplinary group with engineers, computer scientists, oceanographers, and geologists involved in the project, with some actions as developers and others in the validation of the modules. The underlying names are master's and doctoral students who typically participate in both activities. CASI is a flexible and scalable web tool based on JavaScript and Google Earth Engine, 100% based on web process and open source code. We developed applications that bridge the gap between Google Earth Engine and the users. We have four modules today: shoreline, bathymetry, coastal squeeze, and the intertidal tidal flat topography. The last three are in beta versions. In the shoreline change analysis module, we use the normalized difference water index to define the boundary between land and water, as can be observed in the slide. This is the product, the final result. Shoreline change can be obtained anywhere in the Brazil or in the world as you want. The second module, beta version, is the coastal squeeze module, where coastal squeeze is the coastal compression process caused by the occupation of the coast and the sea level rise. The occupation may be blocking the natural migration of mangroves, causing their compression, and this will reduce the morphological and the biological zoning. To do this, the first step is to account for the boundary between water and vegetation, the shoreline. And the second step is to define the urban boundary. And then we have the mangrove area evolution and projections. Here we have an example of how it works in the system. First, we select two images from different dates among all the available images over the last 40 years. Subsequently, within the chosen area for analysis and future projection, pixels with mangroves, water, urban area, and vegetation are selected for machine learning algorithm training, the random forest, that is based in a supervised classification. Sorry, this slide is in Portuguese, but at the end, for each transact, similar to the shoreline module, we have the length class for each year. And in this slide, we have an example for 1986 satellite image. And to compare it, here we have the satellite image to 2021, where agua is water, floresta is forest, mangue is mangrove, and urbana is urban area. At the end, we have a squeeze classification, similar to the shoreline module. We use the traffic signal colors. Red indicates a significant squeeze projection. The knowledge of bathymetry is crucial to define scenarios associated with climate change in coastal zones. The bathymetry data serve as a boundary conditions in computational modeling, which requires update bathymetry to predict, for example, flood levels in relation to local hydrodynamics. To obtain this, the third module is the satellite-derived bathymetry in development at this moment. At this stage, an empirical approach is employed, the linear regression model. In other words, bathymetry estimation is performed through regression using in situ data or depth data. To do so, we collect bathymetric data near the passage of Sentinel-2 satellite. Here, in the left side, we have the bathymetric survey grid, and in the right side, the satellite image. Bathymetry was estimated for pixels with less than 15 grams per cubic centimeters of suspended material, with the assistance of the Acolyte software. Here are the results of the eco-bathymeter and satellite-derived bathymetry, using the band ratio between B5 head edge and B3 wing band. From left to right side of the slide, we have the scatter plot between eco-bathymeter and satellite-derived bathymetry. We have the difference between the eco-bathymeter and satellite-derived bathymetry frequency, and plot in space for this difference for the residual. On this slide, to the left, you can see the in situ data interpolate versus the data obtained with the band ratio in the middle. And as you can observe, the result in the CASI in the right side. In order to reduce errors, at this moment, machine learning algorithms are being tested for satellite-derived bathymetry. Using random forest, the root mean square error decreased from 2.37 to 1.07. The knowledge of the topography of the intertidal zone is crucial for predicting the shallow water components of the tide, which in turn significantly affect the estuary morphodynamic and management. The method used here is the waterline. The method uses local tide data to define levels to the waterlines founded for each image on the exact data time, or in other words, for image and tide data. As an input, we have to choose the image collection at different tide levels, highest and lowest, as you can see in this slide. Then we have to identify the intertidal zone using the band ratio algorithm. Then we apply the waterline method to obtain the digital topography model. At this moment, we are conducting topography validation using aerial and terrestrial LiDAR and drones. This validation is conducted in 3 different case studies. Babitonga Bay, that is a microtidal environment with optical restrictions in south of Brazil. São Marcos Bay, that is a macrotidal environment with optical restrictions in north of Brazil, and in a microtidal environment with clear water in New Zealand. After the presentation of the 4 modules of CASSI, now I want to answer this question: what can CASSI do for you with an example? I will show an example of application to define the volume of sediment added to the Balneário Camboriú beach, a beach nourishment project that was conducted in 2021. According to the technical report, it was planned to add approximately 2,500,000 cubic meters on the beach. To do that, we're going to use the shoreline modeling. First, we have to select 2 images, one shortly after they finish the beach nourishment project on December of 2021, the upper image, and another just before it on July of 2021, the below image. Afterward, we compare the shoreline variation change every 50 meters. For example, this results in a table of shoreline variation, as you can see in this slide for Balneário Camboriú Beach. The second step is to obtain the berm height and the closure depth that we obtained from the literature. For this example of Balneário Camboriú Beach, we used 2 meters as the project berm height and 1.7 meters for the wave protect area in the south part of the beach as a closer depth. And we used 3.3 meters for the central part of Balneário Camboriú Beach and 4 meters for the more wave exposed northern part of the Balneário Camboriú Beach. Thus, at the end, when we apply the Verhagen equation based on the Brun's rule to calculate the volume, the final volume is approximately 2,246,000 cubic meters for the whole bay of Balneário Camboriú, when we use this 2 meters berm height and these different closure depths along the bay. If we apply the correction factor proposed by Verhagen for grain size, in this case is very similar, we obtain approximately 2,600,000 cubic meters of sediment for the whole bay of Balneário Camboriú. In other words, we have an error of approximately 10% when we compare to the 2,500,000 cubic meters as proposed in the project. In summary, despite the pixel size issue and associated uncertainties and the processing time regulated by Google, CASSI Core represents an important scientific platform for contribution to the development of fundamental research related to the evolution and prediction of the physical process in coastal dynamics in the context of climate change. Using Google Analytics, we can access the usage of CASSI platform. In the last 12 months, we had thousands of visits in different countries around of the world, as you can see in this slide. Thank you very much. More information about the CASSI Core platform are in the web page. Please scan this QR code